Okay, gang, we're back. Time to talk about weathering in GPH 111. Just real quick, when I say weathering, I'm not talking about weather as in clouds and rain and lightning and whatnot. We're talking about the breakdown of rock. So here's our game plan. It looks simple. What about what weathering is and how it fits within geomorphology, and then the major types of weathering. So what is weathering? The definition is the collective process that leads to the surface and subsurface disintegration and dissolution of rock. The three types include physical, chemical, and biological weathering. So the way I like to think of weathering is if you let something sit out over time, it's going to break down, it's going to weaken. Now, weathering is not, we're not moving anything, so there's no motion involved. It's not like a landslide or a river or anything like that, because it's not going anywhere. Think like a Yellow Pages. If you took a Yellow Page, I don't even have Yellow Pages anymore, shoot. Take your textbook and throw it in a drawer for 100 years. And then open that drawer. And after 100 years have gone by, that textbook is not going to look the same. It's going to have decayed. It's going to have weakened. The dyes are going to have permeated. Let it sit in there for 1,000 years and then open the drawer and see what it looks like, right? And in geology, in geologic time, let it sit in there for 10,000 years, 100,000 years, okay? Things decay and break down over time. What we're talking about in this lecture is how rock breaks down and decays over time. Okay, gang, now let's take a look at this super scary diagram that hopefully is helpful. I built this thing, but it doesn't matter regardless. Let's talk about what we're looking at here. So in the rock cycle, which we've already covered, right, you get sediments that get dumped off into the oceans through rivers. And as those sediments get compacted, they'll form sedimentary rocks. As they continue to get compacted, they'll start getting deeper into the earth and they'll cook into metamorphic rocks via isotopic decay. Eventually, if they get deep enough, they'll melt into magma, right? Liquid rock. And then that liquid rock will form igneous rocks once it gets erupted onto the surface, or just gets in place near the surface in batholiths to form granite. Okay, but the whole thing is, this process is this rock gets pushed onto their surface, we build mountains. And with mountains, you take rock that formed deep in the earth and expose it to the hydrologic cycle. And by exposing that rock to the hydrologic cycle, that is, water evaporates off the oceans, condenses into clouds, and then rains onto these mountains, you put these rocks in contact with their atmosphere and water, that these rocks form down here, it's not stable for them, and they're going to break down and decay. And that's going to form what's known as the weathering front. The weathering front is basically this layer of weathered rock that builds up on the surface of mountains. Now near the top it can be just straight up bedrock that recently was exposed, but eventually you're going to get this layer of weathered rock, a soil. Okay, you can kind of think of it like the scum that would develop on the surface of your textbook if it had been in there for 10,000 years. It's the breakdown of that rock. We're not moving it anywhere. Later we're going to learn about hill slopes that use gravity to move that stuff down into rivers, and then rivers then dump it off into the oceans. That's your geomorphic system. The system is your inputs of tectonic rock. It weathers, it gets hill sloped, it gets transported by rivers, and then the output, it eventually gets dumped off into the oceans. I include a picture of the Sierra Estrella Mountains and the Gila River here to kind of give you a sense for this process in a real example. So hopefully that helps. But all we're talking about here is weathering. Alright, so we got a lot of weathering processes that we're going to talk about. We have chemical, which is hydrolysis, oxidation, hydration, and solution. And then we're going to talk about examples that form from chemical weathering, scrotal weathering, karst topography, and NAMA pits. Then we're going to move on into physical processes, frost action, crystallization, sheeting, and thermal expansion. And then examples, exfoliation domes, and talus slopes. And then we have a little bonus at the end, which is basically biological. Take a minute, and you're going to want to write these definitions down. You're definitely going to want to know these processes. I provided very short definitions for you. So we should be okay. The computer just glitched there a little bit. So you're going to want to pause the video and write these things down. You're going to need to know them. But real quick, before we push on, chemical processes are the processes that involve chemical reactions. Okay, so you're going to be chemically breaking down or altering the chemistry of the rock. The rock itself changes. So like in oxidation, it breaks down through contact with oxygen. Okay, the oxidation process rusts iron-bearing minerals. It turns them into red and clays and breaks them down. Okay, typically though, chemical processes round things off. Physical processes, are actions like boom, something happens to that rock and it will fracture and break, and it will generate highly angry. So here's our weathering processes for chemical weathering that we're going to talk about, and their associated weathering landforms. Hopefully you've already written down the definitions. Okay, hydrolysis. Hydrolysis is this all happens at a scale that we can't see. Minerals chemically combine with water, and basically the silica gets substituted for hydrogen, and it basically weathers individual weathering grains. So as you look in here, these pits that you look in this rock, okay, these are feldspars, rectangular minerals that are getting eaten away as water gets substituted for silica, and it decays those minerals down and turns them into dissolved minerals and clay. Okay, it breaks it down. What's fascinating about this process, though, is that it removes a tremendous amount of CO2 in the process. Okay, carbonic acid is a key ingredient in allowing this process to take place. Carbonic acid is just carbon dioxide and water. So this process leaches CO2 from our atmosphere. And if our planet, basically our civilization, stopped putting CO2 in the atmosphere, eventually our planet would cool off because we have such huge mountains that exist on the planet. We would move into another ice age. But that's not happening right now. We have the opposite because we're putting tons of CO2 into the atmosphere. Okay, oxidation. Oxidation, you guys have all seen rusty things. Here's a rusty railway car. Oxidation is where iron-bearing minerals combine with oxygen. You're going to generate oxides, which is the rust, and softer clay minerals. This is kind of cool. This is a biotite mineral here that's getting in contact with oxygen, and as it rusts, the clays that form in here as a result of this process absorb water. And as they absorb water, those clays expand and they're ripping this mineral apart, okay, breaking it down, weathering it. You see a lot of red rocks on the Colorado Plateau in Arizona. Some of them are, well, most of them are beautiful. This is the Wave in southern Utah. If you ever get a chance, this is a great place to go. This is an ancient dwelling in Wapaki National Monument in northern Arizona. These rocks are red in color because of oxidation processes. Okay, hydration. I just mentioned hydration, but anytime you get clay minerals in rock, those clay minerals can absorb water along their cleavage planes, basically little planes between the clay minerals. They absorb water, and as they absorb water, they expand, and this column here has been heavily eroded because as those clays expand, it pinches out and pushes out the sand grains that are in this column, and it weathers it over time. It breaks it down. The reason I include a picture of Snickers is the reason a Snickers is chewy is because, well, first you got the chocolate, then you got the caramel and peanuts, and then you got the nugget. And in nugget, you got smectite. Smectite's a type of clay that can absorb 10 times its initial volume in water, and that helps make nugget chewy. And so, bet you didn't know that. Okay, solution. Solution's really easy. If you guys drink coffee, anything you put sugar, anytime you put sugar in water, the sugar is going to dissolve, okay? Water is the universal solvent, and it's capable of dissolving 57 of the natural elements. Over half, almost half of the natural elements, water can dissolve. It breaks them down into their ionic forms. So even though you can drink water with dissolved sugar in it and taste the sugar, you can't see it because it's been broken down into its ionic form. Rocks easily get dissolved. So these are all, this is marble, which is metamorphosized limestone. It's getting dissolved by acid rain. This is all these cracks you see in the ground here are from where water dissolving limestone. These pits It's called evualization. It happens at a smaller scale. It's getting dissolved. If you have a landscape that has a lot of solution occurring into the rock, usually it's going to be limestone, because limestone is easily dissolved by water. You can get these caverns in the subsurface. You can even get rivers flowing in the subsurface through these caverns. Okay, like here's a river here, but eventually you could end up flowing down through these caverns. Well, these caverns obviously can collapse. So you can have entire valleys, like this is a valley from where the river used to be, collapses into the cavern, or just little holes in the caves collapse. Or you have streams that pour into the ground as they head into the cavern system. Okay, so very chaotic, unstable terrain. Anytime you've been in a cave, that's not true. Most caves form from solution of limestone, and this is where the water, basically the water is gone when it was flowing through this cavern that dissolved it, and then now as groundwater percolates through the calcite in the limestone, basically reprecipitates, and it'll form stalactites on the surface and stalagmites on the ground. And if this process has a long time to occur, you can get these impressive geologic features in caves, which are absolutely beautiful. These are not so beautiful. At the surface, if you live in an area that has basically karst topography, these caverns in the subsurface that you wish didn't exist, if you live there, they can collapse. So these homes have basically collapsed. These buildings have collapsed into holes in the ground where caverns in the subsurface give way. Alright, so now we're going to talk about chemical weathering landforms. The first one is fjordal weathering. It's fjordal, where chemical weathering attacks all surface areas and it rounds sharp areas into spheroidal shapes. So here's an example. Hopefully I can explain this. This is granite, and this used to be underground, but because a road got built right here, this is a water bottle for scale, because a road got built right here, this underground granite basically got exposed so we could take a look at it. So what we're going to look at is granite underground and the weathering processes that are occurring to this granite. So you can see it has joints. Joints are the fractures in the granite. So we have fractures that are running kind of horizontal, another set down here, and then I'm sure another set down here. And then we have fractures that are kind of running diagonal here and diagonal here. Well, as the water seeps into the surface, it's going to follow those cracks in the rock. And as that water comes in contact with the granite, it's going to have all kinds of weathering processes that we've talked about. Hydration, hydrolysis, oxidation starts to break these rocks down. But because the water is focused along these cracks, that's where it's going to attack. It doesn't attack in the core away from where these cracks are in these blocks. But over time you could see that there used to be a point out here. This used to be like a trapezoid. There was a point here. There would have been a point out here, but that point has been eroded down into a rounded shape. Because weathering was attacking here, weathering was attacking here, eventually those weatherings meet and you round off the sharp edges and you generate round rocks. Now they get rounded off in the subsurface with all this weathered junk around them, but then when they get exposed on the surface, this stuff gets removed easily and you're left with the rounded core stones. Okay, so this is what you get. You get a bunch of rounded rocks on the surface. So in this picture, the fractures are kind of, diagonal of each other. They're forming these triangles. So you can end up with this kind of weird block off by itself. But those that were closer to the old surface that existed when all this was underground, you get really rounded off and just kind of get dumped, poof, and drop down in these places. And this is a Napoleon Dynamite for a new movie that's coming out. I'm joking. This is another rounded boulder that just gets kind of dumped into its area because there was a bunch of weathered rock around it that's removed, and boom, it just gets left there, which is really cool. And then check this bad boy out. It's as round gets. I actually found this when I was having a Who Could Find the Roundest Rock contest with my wife, and I kind of won the game because it was amazing, amazing rounded rock. In this example, you have basically square fractures. They're basically boom, vertical there, and vertical there. I'm sorry, and then horizontal here and horizontal there. Gets attacked on all sides, and this rock is actually still attached at the base. It's not a free rock. It's just got attacked equally on all sides. Just some more pretty pictures. If you ever get a chance, you should go see this. Joshua Tree National Park, absolutely beautiful. We also have them here. You should go and you've never been out to the McDowell Mountains, northern McDowell Mountains is beautiful, sorely weathered granite. What do you call it? Pinnacle Peak is the same way. All right, Nama pits. So Nama pits form where you get these depressions in the rock. Okay, and here's another depression. And they collect with water. So what's neat here is, first off, if you're ever out in the desert and you're thirsty, these things are fantastic. Sometimes, I mean, I've swam in these things before, like a Las Vegas pool. It's fantastic. But what happens is you get a little depression in the rock, okay? And then rain lands in that depression and sits there. And then the rain, the water, decays the rock. It weathers the rock through chemical processes. Then once the water evaporates, it's gone, the wind blows, right? It erodes that weathered material away. And now that hole's a little bit deeper. Then the rain gets in again, weathers a little bit more, wind blows it out, and it gets deeper and deeper over time until you can end up with this like pothole here, or this kind of broader infinity looking Nama pit here, which I love that picture. Here's another one. This is the incise meanders of the San Juan River and Monument Valley in the background, geomorphological wonderland. Okay, so let's talk about physical weathering processes. So in physical processes, remember, we're breaking it down. We're not rounding things off, we're breaking sharp edge stuff. Okay? First one's frost action. It's frost action. So in this example, it's really cool. We got this lake here, and then you can see we have these like rocks that look like tiles, right? You could use these to build a house or build a floor with. And again, we have fractures in the rock that are very square. Okay? But when water seeps into those cracks and freezes, the water expands. Okay, it'll expand in volume by 11%. And when that water freezes, typically at night, it exerts a tremendous amount of pressure on the rock when it freezes, and it will break it apart. It will shatter it. And that's what all these rocks here are. Let me give you another look at it. Here's looking at it at a side angle, right? Look at all these tiles that have been broken off. Here's another example from frost action. Cool process. This is a giant boulder. I would stand to about here, and it got dumped here by a glacier. Maybe frost actions shattered into this giant pieces. I don't know. Looks like a massive cleaver crushed this thing, but absolutely beautiful nonetheless. Okay, so a weathering landform. Remember, chemical weathering, round stuff. Physical generates angular. If you have a pile of angular rocks, like this, or there's a bunch of it here. I mean, all these slopes are piles of angular rock. Those rocks got there from physical weathering. Now, they didn't get there. A hill-slope process transported them, but they were weathered. They broke from the bedrock through a physical process. That's why they're angular. A pile of them is called a talus slope. All right, next one, crystallization. Crystallization is a lot like frost action, except when the water gets into the rock, into the crack, instead of freezing, the water evaporates. And when the water evaporates, all the dissolved salts in the water will crystallize. They form their mineral form. They come out of their ionic form, and they form crystals. And again, those crystals grow bigger than the water, than the space the water is in, and it breaks it apart. Okay, it destroys the rock. You get the same thing if you ever like leave water in your glass here in Phoenix, and all the water evaporates. You end up with this kind of white rind on the inside. It looks gross. That's salts. Those are the salts that are left over. If you put that stuff in these cracks in a rock, it's going to rip it apart. Okay, sheeting. Sheeting is where buried rocks are under tremendous pressure, and once uncovered, pressure drops sharply and the rocks rebound. The pressure drops sharply and the rocks rebound. So what I mean is this rock was deep underground, but as it comes up to the surface, so much pressure got removed that the rocks kind of go boo. They bow upward and break into a series of sheets. And these sheets, the fractures are parallel to the surface of the ground because that's where the pressure was released as the rocks kind of bow upward. This is in Yosemite National Park in California. This is at the bottom of the Grand Canyon. You take weight off rock and it will break upward into a series of sheets. You can form big landforms called exfoliation domes through this process. This is a big dome, Enchanted Rock in Texas. Basically, As all the rock got removed, this rock kind of bows upward, this granite bows upward, and sheets of it break off parallel to the surface. This is Half Dome in Yosemite National Park in California. Same thing. These are people climbing up the side of it, but you can see the massive sheets that rip off this thing, and they do still rip off this thing today as it weathers. Okay, thermal expansion. So what happens in thermal expansion is a fire comes through an area, hits the rocks, okay? And as the fire goes through, any kind of water or moisture that was in those rocks, it flashes the steam, and as that stuff flashes the steam, it will explode rocks. So it's a very violent process. And nobody ever gets to see it because nobody's around in the fire. Here's a small example where this quartzite cobble has a bunch of pieces that popped off of it through a forest fire that went through the Mosasol Mountains in Arizona. Here's another example of a big boulder, but the main one here, and that's what these guys are laughing about, is my old advisor at ASU did a study where he was studying granite boulders out in the Sierra Sanchez Mountains, and a fire went through, and he was looking for a boulder he was doing a study on, and the reason they're laughing is because his kids can't find this giant boulder, and the reason they can't find it is because it's all these pieces on the ground. It exploded into chunks that were fist size when it was an absolutely huge boulder. It's always good for a few laughs. Here's another awesome example. So here's a pointy rock right here. There's actually a giant landslide out there in the background, but don't worry about that. This big rock, this big granite boulder sticks up, but the top of it has a lot of fresh weathering on it. It doesn't look all varnished like here, like rocks typically do in the desert when they're exposed to the atmosphere. The reason why is lightning keeps striking the top of this rock over time, and obviously the heat flashes water to steam and heavily decays and weathers the rock. You can also get thermal expansion through differences of day and night cycle. This one's debatable. We're not exactly sure if this happens, but you can find rocks out in the desert that break into these patterns where this axis is parallel, or I guess perpendicular to the highest point of the sun. And so it seems like maybe this happens during the hottest time of the day, where it gets hot enough for that water to flash the steam and break rocks apart. Okay, our bonus is root growth. So as you can imagine, here's this little teeny tree with a giant root, and it's just ripping this rock apart, right? This rock was down here, and it's got lifted up and broken apart. So life is on our planet, and life obviously is going to have a huge impact. Plants, lichens are these guys here, will decay and eat at rocks and break things down. Here's another cool picture where there used to be a giant rock here, and this root growth basically made it unstable, and it cascaded down, and the little bush wins. It beat the rock. Here's another example. I'm not going to go into any more detail on those, just let you know they exist. Take a minute and think about this. So if you're in these different places on Earth, if you're in the Amazon, if you're in the Serengeti, Death Valley, Minnesota, Sierras, or Alabama, if you guys could just take some time and think about this, it's a good way to get you prepared for the exam. Just think about what type of weathering process would dominate in the Amazon, would dominate in the Serengeti and Death Valley, and we'll talk about it in lab. So I would stop the video, jot down your ideas, and be prepared and bring it into class next time we have lab. Okay, our last concept we need to cover is surface area. So surface area is, well, the importance of surface area. So all I mean by surface area is, here's this giant boulder that almost crashed onto my car. I mean, it came down. I was just like, no way. No, I'm kidding. They just built a road underneath it. But the surface area is like all the stuff that's on the surface, right? But there's a lot of rock inside that's not exposed on the surface. But if you took this rock and you pulverize it into a bunch of rocks that size, you expose a lot more of that rock. You dramatically increase the amount of surface area. So the general idea is, the more surface area you expose to the atmosphere and water, the quicker it's going to weather down. So a huge boulder is going to weather much less quickly than a bunch of smaller boulders, okay, or smaller grains of rock. The smaller it is, or the smaller you pulverize, or the if you take a big rock and you pulverize it into a bunch of small stuff, you dramatically increase surface area. that allows weathering to attack a lot more surface area and break it down. An example would be is if you ever make coffee, if you put coffee beans in a coffee filter, put hot water through it, you would end up with extremely weak coffee. But if you take those coffee beans and you grind them down, you've exposed the insides of those coffee beans a lot more. You've dramatically increased the surface area. If you pour hot water through that, you'll get a lot more chemical reactions and you'll get a much better cup of coffee. Okay, so the greater the surface area, the greater the amount of weathering. And the kind of point of that is if you kind of combine them, and here we're just going to zoom in on the geomorphic system. And these weathering rocks, if we combine chemical weathering and physical weathering, the physical weathering is that, bam, that breaking part, right? We're breaking into smaller pieces, breaking into smaller pieces. And the more you break it into smaller pieces, the more water can get in there and the atmosphere can get in there and really breaks it down, okay? So the two kind of work as a tag team to really break down the rock on the surface of the earth. An example of that is if you were going to suck on a candy like a mint, and if you didn't bite the candy and you just sucked on it, it would take like, what, 10 minutes for you to finally finish that candy if you were just going to suck on it. But if you sucked on it and chewed on it, if you did the physical weathering of crunching it with your teeth, and then, which dramatically increases surface area, then you've opened up the inside of that mint to your saliva, which is gross, which helps break it down much, much quicker. Okay, so the two processes kind of work in tandem. So fundamentally, what does weathering do? It's the in situ breakdown of rock supplied by tectonic rock input. Don't worry about isostatic, I'm nerding out there. Just tectonic, right? This rock that as we build mountains, so that rock comes up, it gets exposed to our atmosphere. It's the in-place breakdown of that rock. It forms this rind on the surface of the earth. Okay, so here's our things to know. I need you guys to know what weathering is. Chemical processes that round edges, physical processes generate angles, the different types of chemical weathering and associated landforms, types of physical weathering and associated landforms, and then the importance of surface area. And that's all. That's it. That's all I need you guys to do. So have a good one, and look forward to seeing you in lab.